Hello, good afternoon. Yeah, sorry, this Khandwa road, you cannot tell how much time it will take. There was a long jam, so we had to go inside the village and come. Okay, so like I said, we did lecture 1 intro on machine learning and then regression introduction, where we did one simple regression as well besides correlation. And of course, now the question was multiple linear regression, which we had started, and how to solve it numerically in closed form and then regularization. But some of the concepts which are going to show up in this require a little bit of optimization. So I thought I'll go over it as a lecture for you, those who are completely new. I mean, besides the CS undergraduates who have taken optimization with me. So that's the goal for today. On the drive, so what I'm following is these two lectures, earlier one there and all the recordings are already there. I'm following the offline supporting material. Hai na? Did you guys attempted this homework 1 from last class? Alpha, beta, were you able to do it? Sorry? Yeah, okay, all right. So you can start looking at the practice problems also, which are there, although you will be able to do it after Wednesday, all of it. Hai na? So in terms of supporting material, the first one was ANN, which like I said, we're not doing in the class because CS undergraduates have done it and it's out of scope for a machine learning class. So what we're going to do is go over these PDFs today. The way I've segregated them is 2A, 2B, 3A, 3B, and 4A, 4B. So what we are doing is I'm just reminding you a little bit of linear algebra in 2A and 2B. In 3A and 3B, this is introductory optimization, or you can say multivariable calculus. In that sense, we are reminding you. And then we'll see a little bit of unconstrained optimization today. Then we'll finish the 2 regression lectures, and next week onwards, we have to start support vector machine. There I'll take another lecture on optimization, which will be slightly more involved than what is today. And then we follow. Okay, so the first 2 PDFs, I'm not going to spend too much time. What I want to spend more time is unconstrained optimization. This is more of a background. I'm just going through it. I'm not teaching you this. I'm just going over it so that when you sit at home or in your hostel and go over it, you should not get lost. And you should know what to study. Because if I start teaching it, it will take 2-3 lectures. So I'm giving you an outline. Okay. So linear algebra, in case you have forgotten, you can go back to your undergraduate notes and remind yourself a little bit about rank, range, matrices, solving linear system, consistent set of equations, and so on and so forth. LU factorization, eigenvalue problem, all that which is taught in the first year, if not first year, the second year engineering anywhere. If you're sciences, you can take help from the TAs and they can guide you on the material. So you can come to us, don't get lost. What is not taught in the undergraduate linear algebra is what is a positive definite matrix. I mentioned this last time, but I'm going to go over it more in detail. So you can read there's a motivation of giving a definition for what is a positive definite matrix. So the definition says, for a real symmetric matrix, the following statements are equivalent. When you say equivalent, in mathematics, equivalence means if and only if condition. A implies B and B implies A if and only if B. So that is what is an equivalence condition. So if you look at the definition, it says, the very first thing it says is for a real symmetric matrix. So positive definiteness by definition has been defined only for symmetric matrix. Symmetric positive definite matrix. So that's one thing to remember. That's how it's defined. It's something like defined. No, we're calling this as a day. We're not calling it as night. We can call this as night. No, why to? I mean, it's just a word. So it's a definition how you define it. So the definition says that if for every non-zero x, which means that A is an n cross n matrix. We are working with square matrices in this. So we are not talking about rectangular matrices. This square matrix, if you multiply with a vector x from the left, like this is, and then multiply with the vector on the right, what will be the dimension of x transpose Ax if A is n cross n? 1, it will be scalar. Everybody agrees? It's 1 cross n cross n, and n cross 1. So it's 1 cross 1, it's a scalar. So the scalar which comes out, if you take a matrix and multiply with a horizontal vector on the left and a vertical vector on the right, if that scalar is positive, we call the matrix as positive definite. It's saying x should be non-negative, or x should be greater than 0, not to be equal to 0. Why? Because if it's 0, then the whole thing will become 0. In that case, the matrices are called positive semi-definite. So the word semi adds in if you make this equal to 0, greater than equal to 0. So that's the word. Positive definite matrices are the nicest matrices you could work with because they have very good properties, and rest of it is the properties of the matrices. The very first thing is that the eigenvalues are positive. In case you have forgotten what an eigenvalue, I'll say go back to your linear algebra and revise it. We'll leave this Kolesky factorization because then I'll have to go into details. The leading principal minors are positive. All principal minors are positive. So those are characterizations, different ways of defining. Sometimes it's difficult to prove the general definition. So then you fall back on these characterization. You find the eigenvalue or you find the minors and so on and so forth. Everybody knows what minors are. In case you don't know, go back linear algebra and find it. Okay. Leading principal minor means like if finding the minor of the first element, I'll leave the first row and the first column and take the remainder of the submatrix, find its determinant. So that's called the first leading principal minor. Similarly, there will be a minor for every element. Is that okay? Go back and revise. So that's one thing about positive definite. You can read it. Another thing which we're going to use is something called as a pseudo inverse. Now what is a pseudo inverse? So matrices which we study mostly are n cross n, square matrices. What if you end up with a rectangular matrix which is m cross n, which means either the width of the matrix is longer than the height of the matrix or the vice versa. So in that case, is the inverse of the matrix defined? So the answer is yes. It is called a pseudo inverse. Pseudo means approximately. Pseudo, the word English means approximate inverse in that sense. So what is a pseudo? So we're going to run into these matrices in a regression problem. That's the reason I thought I'll bring it to it. So like in all of the math, you define something first. So you have to define what is the pseudo inverse for a rectangular matrix. For a square matrix, we know it's a normal inverse, which we call whether the inverse exists or does not exist. No, if the eigenvalues turn out to be one of them is 0, you'll say it's not invertible. Inverse doesn't agree. If all eigenvalues, none of them is 0, then the inverse exists, and you're good on a known domain. But when you run into a square rectangular matrix, then we have to define what an approximate inverse means. So this is the definition. It says a pseudo inverse which satisfies the Moore-Penrose conditions. Again, Moore and Penrose were two people who came up with these conditions. So it says if A is a matrix, X is an inverse, AXA should be A, XAX should be A. If you take the conjugate transpose of it, shouldn't change. If you take the conjugate transpose of XA, it should not change. But eventually, I'm going to skip all this because there's a little more math in here. This is how a pseudo inverse is defined. And this is dependent on the rank of the matrix. What is the rank? Sorry? The number of linearly independent rows or columns you have. If you're looking at row rank, you'll say the number of linearly independent rows. If you're looking at column rank, you'll say the number of linearly independent columns. So here we are looking at the rank of the matrix. We're saying if the rank of the matrix is n, which is smaller than the other dimension, then this is how it's defined. Otherwise, this is how it is defined. Is that okay? You can study more about this. It's talking about singular value decomposition here. You can skip that. It's not needed for this course. You should just know that for rectangular matrix, inverses are defined. These are called approximate inverse or pseudo inverse, and this is how they're given. Is that okay? So that was basic linear algebra. Then going to introductory optimization, the next two PDFs. One is gradient and what is a Hessian, and then what is convexity. These are the two things I briefly talked about in my second lecture when we talked about regression. I talked about a gradient. So we'll just go over them. and then you can practice them at your ease. So the very important thing, like I said in the regression class, where I said it in a hurry because these guys would get bored, otherwise the CS people who have done it multiple times, is that we're looking at function of many variables, which means that the domain of the function is n-dimensional rather than one-dimensional. Typically in your basic entry-level calculus, you just do f going from R1 to R1. It's one-dimensional domain, one-dimensional range. That's what when you got a function of many variables that the domain is n-dimensional, then what happens, what's the generalization of a derivative? Because now there are multiple variables there, x1, x2, x3, xn. So the generalization of a derivative for a function of many variables is called a gradient. That's what's written here. If it is continuous first order derivative, this if confuses you, ignore it. You're taking partials of the function with respect to the variables and putting it in a column vector. By nomenclature, gradients are put it in a column form. I mean, you can put it in a row form, nobody complains, but that's how people do it. And it's written as an inverted triangle. That's how we called it, as the del or delta or whatever you want to call it. This is how gradient is defined. Now, if this was a function of one dimension, then if you take the second derivative, you will write d2f over dx square, correct? Now you have to do the generalization to the second dimension of a function of many variables, then that's called as a Hessian. So what you do in a Hessian, you take every element of the gradient and differentiate with respect to all the variables. So you take df over dx1 and I'm going to differentiate with respect to x1 to xn and put it in a row format. I'm going to take the second guy df over dx2, differentiate this with respect to x1, x2, xn, put it as the second row. So that is how you're defining something called as a Hessian. If Jacobian confuses you, ignore it. I'm just telling you how to go from the gradient directly to the Hessian. So this you can see you are taking all the partial derivatives and writing them there, and that's how it's the equivalence of a function of many variables with a second derivative. Everybody okay? This is what we're going to use more in optimization, okay? An important thing to note here is that if your function is continuous up to the second derivative, again, if you've forgotten about continuity, please go back and remind yourself what a continuous function is, what is a continuous derivative, what is C0, C1, C2. C0 means that the function is continuous, C1 means that the function is continuous up to the first derivative. The first comes the function continuous, then comes function differentiable, then comes the first derivative of the function is continuous. Then it will be the second derivative existing, and then it will come the second derivative being continuous. So in case your function is C1, which means it's continuous up to the first derivative, then d2f over dx1 x2 would be equivalent to d2f over dx2 x1, which means that these two guys, this guy and this guy, will be same. Similarly, so which means that this will build up a symmetric matrix. Is that okay? Everybody come. This concept we're going to use in optimization. This is what is written here. There's a little bit note about Taylor series. Although I don't think we're going to use this in machine learning, it's always good to know. Taylor, of course, being a French mathematician beyond, in the 1700s and so on. So we wanted to know how a function behaves around a region. So you start building an approximation of the function by taking its derivatives. So if you were working in one dimensional, the Taylor approximation of f at x plus delta would be fx plus delta f prime, f delta f double prime. F prime means df over d, df over d square. It's a function of one variable, so we can write it f prime and f double prime. Everybody okay? Now when you working with function of many variable, this characterization changes. You can see if you're working with function of two variables, you'll have to have the two partials playing a role. So instead of df over dx1, you'll have both df over dx1, df over dx2. We are taking the first derivative equivalent. Then you take the second derivative equivalence, you'll need to have all the partials, the second partials. So d2f over dx1 square, d2f over dx2 square, and the middle term which is added up assuming that f is c1, which means that it's continuous up to the first derivative. Everybody okay? So in general, how you can write it like this. In general, approximation of a function f around x plus delta is fx plus delta transpose gradient of f(x) plus half of delta Hessian. So the more number of derivatives you carry, the more accurate representation of the function you're trying to do. So if you write just the first derivative, it's little crude. If you take the second derivative, it's more accurate. You take the third derivative, it will be more accurate. But for the sake of this class, we usually don't go beyond the second derivatives. Everybody okay? Yeah, so I think there's some problems on it. You can practice them because this is going to stay in regression, a lot of it, and in support vector machine, which we're going to do the next 5 lectures. So it's important that you don't get confused on gradients and Hessians at least, please. Huh? So go and practice this. Moving on further, convexity. In case you have seen it before, that's okay. In case you have not seen it, I'm going to just briefly tell you what it is. What is a convex? You've seen convexity from physics, right? Assuming that everybody is a science graduate, you've taken science. You used to have the convex lenses and you used to have the concave lenses. Remember, you would do experiments with it. So the idea is similar in functions. When you say something is convex, it means that if you take 2 points on any curve and draw a line, the function stays below the line, right? Or if the function is like this, we'll say the negative of the function is concave because I'll take f, I'll take minus f and it'll invert it. It'll take a mirror image across the x direction and it'll draw a line and then still the function values will remain. So you want to write this mathematically, which is written on the screen. It's okay. Before we talk about convex function, we need convex functions are defined on convex sets. Now, what are convex sets? Convex sets mean that you take any 2 points in the set and draw a line. Every point on the line remains in the set. So that is what's written here. If you look at the first figure, you take 2 points and every point is inside the set. It's a convex set. But if you take this guy and take 2 points and draw a line, the line goes out of the set. Yes or no? If I'm going too fast, you tell me. This is very introductory, so I'm just breezing it over. Everybody okay? Is it fast for you? No? Stop me and ask me questions if it's confusing you. So here the line goes out of the convex region, which means that this is not out of the set, which means that this is not a convex set. So now we talk about what is a convex function. The way I've drawn it, I can only show you it in 2 dimensions, but this works in n dimensional as well. So to write it in n dimensional, this is how you write. Alpha x plus 1 minus alpha y belong to set. This is the equation of the line. Now x is n dimensional and so is y. Alpha is a scalar which is deciding where you are on this line. Everybody okay? So now coming to convex functions. Convex function, I already defined it for you. You can, I'll come to the definition, but if you look at this figure, the first figure is convex. You've taken, the set is convex first of all. Convex functions are not defined on a non-convex set. This is how the definition goes. So the set in this case is, let's say, all of the real space, and we're showing you in 2-dimensional x and y. This is the curve. You draw a line. The curve stays below the line, or the surface, hypersurface stays below the hyperplane in an n-dimensional, then it's a convex function. If you look at the second figure, again convex, nothing changes. But if you look at this third figure, you can see sometimes it's going up and sometimes it's going down. So which means that it is not a convex function. It is not even a concave function. We usually don't study a concave function because we just say take minus of f and show that it is convex rather than proving something is concave. Everybody okay? So now the definition of it, because in 2-dimensional you can visualize it, but n dimensions you can't visualize it. So the definition goes like this, that if you take f of this, if you look at the left hand side of something which is highlighted in yellow, the inside of that is the equation of the line. So if saying the function value of this equation of the line is of the function between this set of points is less than alpha x plus 1 minus alpha I. So if you want to look at this way, what it's saying is this guy, f of alpha x plus 1 minus alpha I, this is the equation of the curve. And the right hand side, alpha x plus 1 minus alpha I, is the equation of this line. Or this is hyperplane and this is the hypersurface of the function. Everybody okay? So understanding by visualization is okay, but while working it out mathematically, you'll have to use the definition. Everybody fine? Now, like I said, for the positive definiteness, no, a function symmetric matrix is positive definite if for every non-zero x transpose Ax is greater than 0. So that's a difficult definition to work. The characterization for that is all leading principal minors are positive. All eigenvalues are positive. So similarly, in this case, there is a characterization of saying that a function is convex, and that characterization is find the Hessian of the function. So if the Hessian of the function turns out to be positive definite, then we say that the function is strictly convex. If the Hessian of the function turns out to be positive semi-definite, then we say that the function is convex. So there is a slight difference between convexity and strictly convex. When you say convex, which means that it could be the line or any surface below it. When you say strictly convex, it has to be below it. So if there is no equal to sign here, it will be a strictly convex function. If it is an equal to sign, then it will be a convex function. Everybody okay? Yes or no? So here actually we have proven a lot of things. You do this so that you get comfortable with convexity, please. Hai na? Solve these problems and you understand it at home. Problem 1, problem 2. The characterization, I think, this is what I have written. A function is convex if and only if. When I put an equivalent sign, it means if and only if, which means it goes both way. If the Hessian of the function is positive semi-definite, it is convex function. If it is a convex function, then the Hessian is positive semi-definite. Everybody okay? When I write strictly convex, then I'll drop the semi-predicate. I'll just say a function is strictly convex if the Hessian is positive definite. If the Hessian is positive definite, then the function is strictly convex. Everybody okay? Why are we so much after convexity? Because it's the nicest property. Like positive definite is the nicest matrix you can work with. Convex functions are the nicest functions you can work with in all of engineering. Take any science or engineering, because any minimum value becomes a global minimum value for a convex function. You can prove it. So that is why we are after convex functions. Everybody okay? We'll use this fact in regression. In fact, I told you in the last class that for the simple linear regression, when we did f prime and f double prime, and I said, when you will see that f prime is equal to 0, you will get candidates, the alpha and beta, which you did in your homework 1, correct? I said these are candidates for minimizer, these are not the minimizer. When you take the second derivative and show that it's greater than 0, then you can prove that it is a minimizer. And if that second derivative is positive everywhere, irrespective of the point where you're finding the minima, the stationary point, then it is convex function and it's a global minimizer. That's where we're going, the 3 layers. This concept will be reinforced tomorrow when we do multiple linear regression. We're going to do a homework on that as well, okay? So what we did positive definite pseudo inverse gradient Hessian convexity. Now I'm going to get started on unconstrained optimization, which is needed for regression. The constrained optimization is needed for support vector machines, which we'll do next week. Okay. Where are we? Okay. So what I'll do is you go through, I've selected certain set of notes and uploaded this on the drive. I'm not going to go over all of these notes. You go read it at your leisure. so that you get comfortable with it. The more time you spend, less foreign it becomes for you in case you're seeing it for the first time. That's why I'm saying read it by yourself. But what I do want to emphasize is something which we're using in regression, and I'm going to use it tomorrow again in multiple linear regression, which is the necessary and sufficient conditions for a minima. So these are all parts. This is a little motivation, formulation, recognition. I'm going to skip all of this. Unconstrained optimization. So just one. So anything above it is very straightforward. Please read it by yourself. It gives you introduction to optimization. So let's start with unconstrained optimization. So first we define what is a minimizer. So if x star is a global minimizer, which means that the function value is minimum everywhere. If x star is less than fx for all x. It's unconstrained means there is no fixed region. All of the real space, Rn space. When I say Rn space, the real line in n dimension. So you're looking at this way. It is said to be a local minimizer if fx star is less than fx in this particular vicinity, which means you take the point x star and draw a hypersphere around it. However small it is, it could be, the radius could be 10 to the minus 100. It could be as small as. If you are minimum in this very small region everywhere, then use the local minimizer. Is that okay? So that is how we define it. And that's what it's written there. This is how you write mathematically in case you've not seen it before. There exists an epsilon such that fx star less than fx is less than fx in x minus x star less than equal to epsilon. So x minus x star epsilon is referring to this epsilon radius hypersphere, and you are at the center x star. If any direction you go from x star, the function value starts increasing, then you're good, you're minima. But if any point you go any direction and the function value starts decreasing, which means that you are not a minima. Make sense? Okay. This is another characterization. This weak and strong will just tell you. If you say fx star is strictly less than fx, then we say it's a strong local minima. If it is equal to, then it is a weak local minima. Is that okay? That's what's written, weak and strong here. Okay. Before I start the necessary condition, now look at this figure. If you look at this figure, this point is a strong local minimizer. I'm showing you in 2-dimensional, by the way. Use a pen. So if you're at this point and you go anywhere direction, the function value increases, which means that it's a strong local minimizer. It's local because I'm looking only in the vicinity, only in this region. When you look at this flat line, again it's a local minimizer because it is from this guy to this guy, but it's weak because in the neighborhood you have the same values. Everybody is making sense? This is a strong global because you can see that the function value is going up everywhere. Globally it is a minimum value. This is a minimizer and this is a weak global minimizer. The x-axis is a minimizer. These are the minimas, the fx value. Everybody okay? Now coming to the most important thing, which the reason I took the class is the necessary and the sufficient conditions. So I'm going to give you the characterizations of what you have seen in your one-dimensional case. When you have to find a minima for a function going from R1 to R1, you say f prime or df over dx is equal to 0. Everybody agrees? That's what you do. So now in the function of many variables, where f is going from Rn space to R1 space, then it means that the gradient is equal to 0. That is what the definition says. So I've written it here. Recall from R1 to R1, x star is a minimizer if fx star is equal to 0. It's a necessary condition. What is a necessary condition? It has to be definitely true, but it is not sufficient enough to make it definitely true. right? If you are, like I give it in my optimization course example, that if you are, what is the necessary condition for getting admission for a computer science major at IIT Indore? What are the necessary conditions? Can you tell me? Sorry? Tell me. Is there only one necessary? You should pass 12th with your physics, maths, chemistry. Earlier there used to be a percentage also. I don't know whether it's there or not. You should sit for JEE mains. You should get rank in 100,000 students in JEE mains. You should sit for JEE advanced. You should get a rank in top 1000 in JEE advanced. You should come for the counseling. You should pay your fees. I mean, all these are necessary conditions. Because any one of them will fail, which means that you are not admitted to computer science, right? When all of them put together, they becomes the sufficiency condition. You 12th, JEE mains, JEE advanced, come for counseling, give you card, join the institute, start taking classes. All of that together will form the sufficiency condition, right? So necessary conditions is you negate one and the answer becomes a no. Right? So if it is a minimizer, f prime of x is equal to 0 was a necessary condition for finding a minima. It was not sufficient, which means f prime x equal to 0 could be when it's a maxima, when it's a stationary point. It could happen in many cases, but it's the first step. So, but the equivalence for going from Rn space to R1 space is that the gradient is equal to 0. Why? Because the equivalence of the first derivative for a function of many variable is the gradient, which in case you didn't know earlier, now you know. Everybody with me? So in my class I proved this also. You can skip the proof. You don't need to know. You just need to know that this is a necessary condition. Now when we go, this is called the first order necessary condition. Why is it called first order? You're taking first derivative. No, what is gradient? Gradient is the first partials of f with respect to the variable. That's why it's the first order condition. Similarly, there could be a second order condition. Map it to admission to IIT Indore. No? The first order condition is JEE mains, sitting, clearing. The second level conditions are JEE advanced and so on and so forth. So similarly, there is a second order condition, which I will not go second order necessary because what we are after is the sufficiency condition. So I'm going to skip this. I'm going to the second order sufficiency. So the second order sufficiency says ignore that f is C2 in an open neighborhood of x star. This is a mathematical reason why we do it, and I tell my computer science students you can ignore it for the moment for machine learning class. But what is important, it will carry the first order necessary condition, gradient is equal to 0, and it carries the second order condition. In the case of f going from R1 to R1, what was the second order condition? F double prime is strictly greater than 0 at the point which you have found by making f prime x equal to 0. Yes or no? So now the equivalence characterization becomes that the Hessian is positive definite. So if the gradient at that point is x star is equal to 0 and the Hessian is positive definite, then x star is a strong local minimizer of the function. Everybody comfortable? The sufficiency condition goes the other direction. The necessary goes the forward. If I am a minimizer, then gradient is equal to 0. While the sufficiency goes that if the gradient is 0 and the Hessian is positive definite, then I am a strong local minimizer. The two together become the if and only if condition or equivalence in case they were same. Here they are not same, so that's why we are not writing it as an if and only if condition. Everybody okay? Yes or no? Okay. So now coming to the last thing which I wanted to emphasize is the applying convexity to this. So in case you are able to first, so what we'll do tomorrow in the multiple linear regression is that we are going to first find the gradient, we'll find the function. What was the function in our case, a regression function? The residue function, right? You were finding y minus y hat and trying to minimize, remember the j, and we were doing it in a least square sense. Forgotten everything? If you've forgotten, go back and see my recorded lecture. We said we're going to find the residue in the least square sense, and I motivated that least square for you. So that's my residue function. Now I have to find the minima of that residue function, where it will arise. So I'm going to take as gradient is equal to 0. I'll get some candidates. I'm going to use that and find the Hessian. If the Hessian turns out to be positive definite, then I'll say this point is definitely a strong local minimizer. Is that okay? But it's still local. What I have also show tomorrow is the residue function which we wrote in the regression, in the simple linear regression and in the multiple, is going to be a convex function. So what you'll do, how will you prove convexity of that function? You'll find its Hessian. You'll find its Hessian, it will turn out to be positive definite, it's a convex function. So now the local minimizer will be a global minimizer. So that's the theorem which I have written here. If the function is convex, any local minimizer becomes a global minimizer. So these are all the 3 theorems which I'm going to use tomorrow. That's why I wanted you to tell it before you tomorrow get completely lost. Why are we playing around with gradients and Hessians? Everybody okay? Okay. Yeah, I think that's it. These are certain problems are there. Please go ahead and practice them. Again, you're finding a gradient, you're finding the first order necessary conditions. So this, if you have time, go over this today itself so that tomorrow when I apply it to regression, you don't get lost. So now what we'll do, we'll finish our regression. Where we stopped in regression, we stopped at the multiple linear regression. We first did the one-dimensional linear or simple linear regression. Now we were doing this multiple linear regression where the domain was multi-dimensional. The range was still one dimension. We were not doing multivariate at this moment. We wrote the residue function. Now tomorrow we're going to differentiate. There are 2 ways of solving it. One is numerically, which we'll see by something called as the gradient descent method. And one is called the closed form solution, where we'll apply these things. We'll find the gradient of the residue function, make it equal to 0, find its Hessian, check whether it's positive definite, check the residue function whether it's convex or not, and whether you get a global minimizer or not. Then we'll finish something called as a regularization in regression, and then we'll start support vector machines. When we start support vector machines, again these theorems will start playing a role, but in a different context. Now how will the context change? You will no longer be working with an unconstrained problem. What is an unconstrained problem? Where there is no feasible region. What is a feasible region? That the constraints are not there. For example, x is greater than 0 is a constraint, which means that you're only looking at the positive half of the plane or the hyperplane. So when you start adding feasibility into the constraints as a constraint into the optimization problem, it becomes a constrained optimization problem. And in that case, all these conditions will change. It will not be as simple as what you saw today. So that I'll revise you next week before I start support vector machines. Is that okay? Again, I have not taught you this. It takes me 2-3 lectures to teach this in an optimization class. I've given you an outline of how to read my notes. Everybody okay? Doubts? Okay, we'll stop here. See? We'll upload this as an extra lecture 1 in the recording in case you want to take a look.